Okay, so now we're going to get into a discussion of periodic properties. So, what we're looking at in this section, actually, is how certain trends occur across a periodic table or down a group in the periodic table for elements and how they're related to the electronic structure of the atom. So, as stated here, as you can see on the screen, there are certain properties, physical and chemical, that recur at regular intervals and or vary in a regular fashion when the elements are arranged according to increasing atomic number. And earlier in this course, we referred to the person who discovered or who came up with the first version of the periodic table, Mendeleev. He was the one who first discovered that if you arrange the elements according to their atomic masses, after so many elements, you see certain properties repeating themselves. Well, back then they had no idea about the structure of the atom, so the concept of atomic number wasn't around during the time of Mendeleev. Now we know that the properties of the elements are more directly correlated to the electronic structure, so therefore that's why they are arranged now in order of increasing atomic number. So when we're talking about properties, of course, we're talking about those defining characteristics, melting points, boiling points, etc. And you'll see that all these properties vary for different elements as you go across a period and down a group, and they tend to repeat themselves after so many elements within a period. All right. So what we'll be looking at are certain specific periodic properties that can be explained according to the electronic structure of the atom. So the first property we'll be looking at is the atomic size as measured by the atomic radius. So first we have to define what we mean by this term atomic radius. Now, it depends on if you're talking about a covalent radius or a metallic radius. In the case of the covalent radius, it is half the distance between the two nuclei that of two identical atoms joined together in a molecule. So if you have two atoms like this forming a bimolecular, if you have two atoms, I should say, forming a bimolecular substance, then the atomic radius, as measured by the covalent radius, would be halfway the distance between one nucleus and the other nucleus, all right? So in this case here, the distance between the two nuclei is 266 picometers. That means that the covalent radius would be half of that, which would be 133 picometers. As far as the metallic radius is concerned, it's half the distance between the nuclei of adjacent atoms in a solid metal. All right, so what do we observe when it comes to variations in the atomic radius going down a group and across a period? Well, firstly, what is observed is that going down a group, the atomic radius increases for the different elements within that same group, all right? And that corresponds to an increase in the n value, meaning basically what period the particular element is in, all right? So within the same group, the elements in the higher period would have a greater atomic size. And that's because the value of n relates to the distance between the valence electron from the nucleus of the atom. Okay, so that's as far as going down the group is concerned. What about going across a period? Well, what was discovered was that going across any period, the atomic radius decreases going from left to right within that period. Why is that so? Well, if you think about it, as you go from one element to the next, what you're doing is two things. You're adding a proton to the nucleus, so the nucleus becomes more positive, and at the same time, you're adding an electron to the valence shell, all right? Now, each electron that is added to the valence shell will be shielded from the nucleus by the inner core electrons. So as far as the inner core electrons are concerned, that doesn't change, right? So what is changing as you go from one element to the next across a period is the increased nuclear charge and the number of electrons on the outer shell, which will be experiencing the same shielding effect from the inner core electrons. So the result of that is that the nucleus, being more positively charged as you go from left to right, will basically exercise a greater pull on the surrounding electrons, and therefore will pull the valence electrons closer to the nucleus, and therefore, as a result, the size of the atom will become smaller going left to right of any period. All right. So those are two things that we have covered so far that you need to remember. Going down a group, the atomic radius increases. Going from left to right, the atomic radius decreases. And this graph here basically illustrates that. Now, let me just say that these trends are general trends. There are some exceptions that you'll observe. But you'll notice what we have here in this graph is a plot of the atomic radius of the different elements versus the atomic number. So this plot right here is basically for period 2 starting with lithium and ending with fluorine. This is for period 3 starting with sodium and ending with chlorine. And then we have period 4, period 5, and so on. And you'll notice that in each case, with a few exceptions, what you'll find is that generally speaking, the atomic radius decreases as the nuclear charge increases or as the atomic number increases, right? So that's why fluorine has a lower atomic radius or a small atomic radius compared to lithium, and the same trend is observed for the others. There are some unusual situations shown here, 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 and here, but generally speaking, that's a trend. All right. I won't go into the explanation as to why we see these anomalies, so we just leave that alone for the time being. Okay. So based on what we have just covered here, we should be able to answer this question. Now, this question says, with reference only to a periodic table, arrange each set of the elements in order of increasing atomic radius. So while you're looking at this, you should be having by your side a copy of the periodic table so that you'll be able to answer these questions. So if you look at the first one, magnesium, sulfur, and silicon, if you consult the periodic table, you'll see that all those three elements would be in period 3. All right? And you'll notice also that of these elements, magnesium is to the extreme left of that period. Now, remember we said going from left to right, the atomic radius decreases. And the question says, and let me underline this here, the question says that we need to arrange the elements in order of increasing atomic radius. So increasing means you start from the smallest and go to the largest, right? So if magnesium is the first one in this series, that means that magnesium is the largest one. So magnesium would be the last element in that series, Mg. And the one that comes, let me see now, sulfur and silicon. So between sulfur and silicon, sulfur would be the smallest because it is the one that is furthest right. So sulfur would be smaller than silicon, which in turn would be smaller than magnesium. So that would be the answer for A. In the case of B, if you look at these elements in the periodic table, you'll see that they belong to the same group. With nitrogen at the top, arsenic would be next, and then actually nitrogen, then phosphorus, then arsenic. All right. So basically, since we know that the atomic size increases as you go down the group, and since we're starting from the smallest to the largest, then the order would be nitrogen first, followed by phosphorus, followed by arsenic. All right. And then finally, in the case of C, where we have arsenic, antimony, and selenium, well, that's a bit different from the other two because what you'll notice is that arsenic and antimony are in the same group, but selenium is in the same period as arsenic, all right? And you'll notice that arsenic is above antimony. So therefore, we know that arsenic would be smaller in size compared to antimony. So we can put that first. And then as far as selenium is concerned, selenium is to the right of arsenic. So therefore, we know that the selenium atom is smaller. So we're going to put selenium here as being the smallest of these three atoms. All right. So that's basically how we do that particular example. Okay. Let's talk about ionic radii. We talked about the atomic radius or radii of different elements. Let's discuss ionic radii with respect to, again, the positions of the elements in the periodic table. Let's first define it. So as you can see on the screen, it says here that the ionic radius of each ion is the portion of the distance between the nuclei occupied that ion. All right. So demonstrated here is um, the formula or the compound magnesium oxide in terms of the size of the radius of the respective ions. So magnesium here, as you can see, is smaller compared to the oxide ion. And as you can see here, the radius of the magnesium ion is 65 picometers, while that of the um, oxide ion is 140 picometers, all right? So the internuclear distance would be the sum of these two, which is equal to 205 picometers. Okay, so how does the ionic radii compare to the atoms from which they are formed? So let's look at what happens when an atom forms a cation. We all know by now that when an atom forms a cation, it loses electrons, 1, 2, or 3 electrons. So how does that affect the size of the cation compared to the size of the atom? Well, what happens is that when the atom loses electrons, the remaining electrons will have less repulsion between them. So therefore, as a result, they'll be drawn closer to the nucleus, and therefore the cationic size would be smaller compared to the atomic size. And you can see that demonstrated in these examples. You see that, for example, the sodium atom is 186 picometers, but the sodium ion, after losing 1 electron, is 99 picometers. So as you can see clearly, the size of the sodium cation is almost half of the size of the atom from which it is formed, the sodium atom. And you see a similar trend when it comes to this other example. Magnesium, the atom, has an atomic size of 160 picometers, while the magnesium ion has an ionic size of 65 picometers. And in this particular case, the decrease is more than a half because of the greater nuclear charge and because the magnesium atom loses 2 electrons to form the magnesium ions. All right, so that shows you the relationship between the size of the cation and the size of the atom from which it is formed. The size of the cation is smaller because when it loses electrons, the resulting ion will have less electrons, there'll be less repulsion between them, they'll be drawn closer to the nucleus, and therefore, as a result, the ionic size would be smaller compared to the atomic size. Okay, then we get to ionic radii. So again, we know that ions that are negatively charged, anions that is, will gain electrons to form the negatively charged ions, or formed, I should say, as a result of an atom gaining electrons to form the anions. So how does that affect the size of the resulting anion compared to the result to the atomic size? Well, it turns out that anions are larger compared to the size of the atoms from which they're formed. And in this particular case, it's basically the reverse argument. When an atom gains electrons, the result would be a greater number of electrons. There'll be greater repulsive forces that would basically lead to an increase in the size of the ion compared to the atom from which it is formed. And therefore, that's a reason why ionic, or I should say anions, will have a greater radius or size compared to the atoms from which they're formed. All right? Now, at this juncture, I want to introduce this term here, isoelectronic, right? What do we mean by this term? Well, basically, an isoelectronic species are basically species that have the same number of electrons, right? Or the same electron configurations, all right? So just to give you, oh, by the way, before I get to that, I forgot to show you this. This basically shows you the comparison between the chloride ion and the chloride atom. And as you can see, the chloride ion is almost twice the size of the chlorine atom. For the reasons I mentioned before, greater repulsion when the atom gains electrons results in an increase in the anionic size compared to the atomic size of the chlorine. Okay, so back to the discussion of isoelectronic species. So as I was saying, when we're talking about something which is, if we're comparing, let's say, two atoms or two species that are isoelectronic, what we're saying is that they have the same number of electrons. So for example, let me just try to squeeze, or let me check. Let me try to squeeze an example or two up here. So for example, if you were to compare, let's say, the chloride ion, oops, the chloride ion to the argon atom, right? They have the same number of electrons, 18 electrons each, all right? And therefore they will have the same electronic configuration. But the difference between them, of course, is that the chloride ion will have 17 protons, while the argon atom will have 18 electrons, all right? But they have the same number of electrons. That's the important thing. Actually, this should be 18 protons here. They have the same number of electrons, so therefore we say that the chloride ion and the argon atom are isoelectronic, all right? Now, that's important for answering some questions we're going to see shortly, but I just want to point out one particular trend which is indicated down here. Let me underline it because it's very important. What you'll find is that the size will decrease with effective nuclear charge. We saw that in effect when we were looking at the variation in atomic sizes going across a period, but that is also true when you compare isoelectronic species. So going back to the example that we saw here, you see that because the chloride ion has 17 protons and the argon has 18 protons, the argon would have a greater nuclear charge, and therefore, in terms of the atomic size, it will be smaller compared to the chloride ion because they are both isoelectronic. In other words, they both have the same number of electrons, all right? So that's the point being made, as I said before, down here, right? Basically, if you have two or more species that are isoelectronic, the one with the smallest radius will be the one with the greater nuclear charge, all right? And you're going to see the importance of that in doing some problems or some examples that we're going to see later on. But before we get to that, I just want to show you this table. I like this table because this table basically summarizes the different trends that we were talking about earlier. So just to point out what these spheres represent, the purple spheres, they represent the atoms, while the gray one represents the ions, or is it pink? I think it's pink. They represent ions. So as you can see here, they give you the sizes. All these sizes, all these numbers are expressed in picometers, all right? So remember we said that the cationic size is smaller compared to the atom from which they're formed. Well, you can see that clearly in the case of, for example, lithium atom compared to lithium ion, beryllium atom compared to the beryllium ion, or down here, the lead atom compared to the lead-2 ion, and so on and so forth. You see that in all these cases, the cation is smaller in size compared to the atom from which they are formed. And then when you look at the anions and their size relative to the atoms from which they're formed, you see that the anions are larger in size. So for example, the nitride ion is larger compared to the nitrogen atom. The oxide ion is larger compared to the oxide ion is large compared to the oxygen atom, and so on and so forth, right? You also see the trends that we talked about in terms of increase and decrease in atomic sizes and ionic sizes as you go from left to right of any period or group, or I should say go to left to right of any period or up and down any group. So if you take group 1A, for example, the atomic size increases, all right? And correspondingly, you see that the ionic size increases as well. And that is true for all these groups. If you go left to right of any period, you'll see that the atomic size decreases. So lithium is 152, beryllium is 111, and you see it continues to decrease as you go down to fluorine, which is 71, all right? So all these trends are captured in this particular diagram. Okay, so, let me point out, for example, when you compare down here between Fe3 plus and Fe2 plus, right? Now, the only difference between Fe2 plus and Fe3 plus is that the Fe2 plus loses one electron to form the Fe3 plus, right? But they have the same number of protons. So the nuclear charge is still the same. So therefore, for that reason, the Fe3 plus is smaller in size, 6 to 7 picometers compared to the Fe2 plus, which is smaller, which is larger, 82 picometers. And of course, the iron atom is even larger because it has no loss of electrons, so therefore its size is 124 picometers. Okay. All right, so let's move on to this example. So in this example, it says refer to the periodic table, but not to the previous figure. So we're not going to look at the previous figure to solve this problem. And the question is asking for us to arrange the given series in order of increasing radius, right? Okay, so first thing you'll notice, or the first thing, well, of course, you need to have your periodic table at hand. So I'm looking at my periodic table right here. And the first thing I notice is that calcium, write it down, oops. Let me get my pen function first. Okay, so the first thing I noticed is that calcium, the calcium ion, the potassium ion, and the sulfide ion are in the same period, all right? Also, they're isoelectronic. They all have the same number of electrons, which would be 18, all right? So I'm just going to write down here. I'm going to write down here Ca2 plus, K plus, and S2 minus. And you'll notice that calcium has 18 electrons, potassium has 18 electrons because these are the ions, and the sulfide ion also has 18 electrons. But you'll notice that the calcium has 20 protons, the potassium has 19 protons, and the sulfide has 16 protons. So what that tells me is that because they're all isoelectronic, but because calcium has the largest number of protons, that means this nucleus is more positive than the others, and therefore its atomic size will be, or its ionic size will be smaller. So therefore the calcium would be smaller in size compared to the potassium, while the potassium would be smaller in size compared to the sulfide, all right? So that leaves now, how do we deal with iron, Fe3 plus, and the selenide ion? So as far as I can see, the selenide ion would be below the sulfide ion in that period, or in that group, I should say. So what that tells me is that the selenide ion is greater in size compared to the sulfide ion. So what I'll do is add to that this right here. Se2 minus would be smaller, would be greater in size, I'm sorry, compared to the sulfide ion. So that leaves the Fe3 plus. Now iron has an atomic number of 26 and has, in terms of the electrons for the Fe3 plus, 27. So let me just write it down here. Let me write it down here. Whoops. Let me write it down here. So for Fe3 plus, it has 26 protons and 23 electrons, right? Now, by virtue of the fact that this has a larger number of protons and electrons, right, compared to calcium, that means that it would be smallest, because largely because of the 26 protons. The 26 protons make the nucleus more positive and therefore will pull the electrons closer to the nucleus compared to all these other atoms. So therefore, what I will do is put Fe3 plus right here. And that would be the correct order of size in terms of increasing radius, all right? Okay, so that's basically how that is done. All right, so we're going to stop here, and the next video will deal with observing and explaining other trends in the periodic table as it relates to the electronic configuration.